Okay, hello and welcome. Today we're going to be talking about calculating work energy problems. And most of the problems, I'll have a bunch of examples, and here's the first question. But I want to talk a little bit more about, just the general framework here. So we're going to be doing problems mostly around the force will be gravity. So we're talking about F is equal to mg, and that's near Earth gravity. So that's the basic physics we're talking about here. We got to know that the work or energy is going to be an equation of force times distance. Okay, those are the basic equations we're going to be talking about today and doing it. So let's start with this first problem. We're going to calculate work to pull up a 1 kilogram bucket up 20 meters. Okay, the cable that we're going to be using is going to be 0.1 kilogram per meter. This bucket's going to start out empty, but the rain is going to fill the bucket at 1 kilogram per 4 meters. All right, so let's just draw a quick picture of what this looks like. Here's our building, let's say. Yep, like that. I'll do a better building drawing there. There it is. And maybe we're up here. We have our cable, and we have a bucket down there like that. And we want to pull this bucket up, all the way up 20 meters. Okay. All right. So what we need to know is, though, is really break down the problem into 3 components. And each component we can compute separately if we want. We want to compute separately. So the first component is actually the bucket itself. And this will be, we'll call this number 1. The bucket itself, of course, is 1 kilogram. All right. And so, of course, the force of gravity on the bucket is going to be just g, otherwise known as 9.8. And, of course, we can multiply this times 1. So a 1g. Okay, so that'll just be 9.8. Okay. And of course, the work done then for just the empty bucket is going to be the integral from 0 to 20 of g dy. Okay, where y then can be the vertical distance from the ground. So the ground starts off at 0, and we're going to go all the way up to 20 right there. So of course that's going to be g times 20 to do that bit of work. Okay, so now let's talk about number 2. So this problem is really a mathematical modeling problem. The integrals in calculus that we're going to be doing are fairly straightforward. Okay, so the first thing we're going to do, the next thing we're going to do now is we're going to talk about the cable. So the cable, I have to figure out what the force is. The force of the cable then is going to depend on the amount of cable out. Okay, so it depends on where the position of the bucket is. And it's going to be basically, it's going to be g times my. And this is the mass of the cable at each y position of the bucket. Okay. So I would like to figure out what my is. And I'm going to come up with this. I'll just state it pretty straightforward. It's going to be, well, we have to know that it's going to be 0.1, and this is going to be kilograms per meter right here, right? Times how much cable is out, and we know that's going to be 20 minus y. All right. And so this is our mass as a function of how much rope or cable we've pulled up, right? So it should be, of course, that m at 0 should be 0.1 times 20, right? And m at 20 should be equal to 0 because there's no cable. We can see that both of these check out. All right, so the work done by just the cable then is going to be integral from 0 to 20 of g times 0.1 times 20 minus y dy, right? Every little incremental step upwards, we lose a little bit of cable, and we add up that force over all those small distances, and we get the work done by just the cable. All right, so I'll leave it to you to calculate this integral. I'm sure you can do it with paper and pencil wherever and whenever you please if you understand calculus. So finally, what I'm going to do now is talk about the rain. Okay, so the rain, we're going to start off again with a force is going to be equal to mg. So this is of the rain. So now the mass of the rain. So what I need to do is figure out what is m of the rain. In this case, it's going to be, again, a function of the height. And that function of the height, I said, is going to gain 1 kilogram per 4 meters. So I go 1 kilogram over 4 meters, like that. And then I have to multiply by how high we are. So that's going to be y over 4. Okay. And we see that the mass of the rain in the bucket at the bottom, of course, the bucket is empty. That should be 0. Check. And the mass of the rain at 20, at the height of the thing, should be, of course, 5 kilograms in total, as we would expect, and everything in between. All right, then the work to pull the rain up then is going to be equal to integral of 0 all the way up to 20, the very top part of it, of 1/4 times g times y dy. And again, I'll let you calculate that on your own. The total work is the sum of all the individual works. It's just going to be work, we'll call it total, be the work of the bucket plus the work of done on the cable and the work done on the rain itself. So all those together. Okay. And of course, you can put that all in one big integral if you want, but I'll let you do that on your own. Okay. So that's our first example of a complicated problem involving a work of pulling something against gravity, where the object that you're pulling against gravity is changing as you're pulling it up. The cable is getting shorter, the rain is filling in the bucket, but the bucket itself is the same mass as all it is. It's just the other things that are changing. All of those things together make a complicated problem that takes a lot of effort to model all the pieces, but when you break it down into each component, it can be relatively simple. All right, so that's our first example. So now what I'm going to do is I'm going to start a new problem. And so this problem, I want to calculate the work to pull a 1 kilogram bucket up 10 meters. The cable, again, is going to be 1 kilogram per meter. And the bucket's going to start with 5 kilograms of water, but then it leaks 2 kilograms per meter. Okay, 0.2 kilograms per meter. So again, this is a leaky bucket problem. I think this is a very classic work integral that's done in many calculus classes. So I think this is something that you've probably seen no matter where you are in the country working out these things. So again, we're going to break down into the pieces. Okay, we have the bucket itself, and I'll call that number 1. So the bucket itself, again, is 1 kilogram. So the force on the bucket is going to be 1 times g, otherwise known as just g. And of course, the work on the bucket is going to be integral from 0 all the way to 10, because we're only going 10 meters now, times g dy, otherwise known as g times 10. Okay, the next piece is going to be, again, the cable. Of course, this is very similar to what we saw before, but now we have to change a little bit of what's going on here. Not much, really. So the force on the cable is going to change as a function of height, so it's going to be, again, 0 times 0.1. That's the mass per unit meter, times g, times, and now it's going to be 10 minus y that goes there, right, rather than 20. And of course, the work done on the cable is going to be 0 to 10 of g times 0.1 times 10 minus y dy. And I'll let you compute that as well there. Not too hard to do. Okay, finally, now we have a leaky bucket. All right, so this is the water in the bucket. Okay, so we have the force on the water, due to gravity, and it's going to be g again, times 5, right? And this is going to be a function of y here. So, of course, that's the 5 kilograms. Kilograms right there. But now what we have to do is take away how much is being taken away per meter. So we take 5 kilograms to start with, but we're taking away 0.2 y kilograms that are leaking off. So this is our leak. Okay, the leak at every point y. Okay, cool. All right, so with this problem here, we want to now, again, the very standard, the work done on the water is going to be 0 to 10 g of 5 minus 0.2 y dy. And of course, I'll let you simplify and actually compute that integral as you would using Wolfram Alpha or by hand or anything. I just don't want to waste video time going over the basic of integration here. It's just not that important. Okay, so now I want to talk about a different problem. So in both of these problems, of course, what's really changed is really the mass was changing. In both of these examples, the mass was changing as a function of y. That was the thing that was changing in both of these problems, in which case you're going to have a function, so really it was an m of y is what you really had to model, was the modeling challenge. And again, this isn't really an integral video. This isn't about computing integrals. This is about building integrals. And that's a very different skill. Computing integrals is a very important skill, but it's not actually nearly as important as being able to build the right integral. Because the building the integral is the skill that a computer cannot do. The computer can actually compute an integral just fine, but it cannot build one. So now I want to talk about a different problem. So now this one's maybe a little bit sillier. I don't know if you think leaky buckets aren't silly, I don't know. But what we have here, we have a situation where here is y equals 0. And I'm going to pretend that there's a 3D printer. And the 3D printer has a little, it can squirt out the little plastic gunk. and it can make, what it's doing is making its own tower beneath itself. And every time it builds a new layer, it climbs higher. So like that. And there's the bottom layer at the very bottom. That's the base. So this is the base, and this is all the layers. Okay, and it just keeps building the tower. Gets higher each new layer. Okay, so the challenge here is that what we're going to describe is really at the very bottom, at the base. What we have is basically the fluid. So the fluid. And we're going to have a little pipe, a little hose that goes up, and it feeds the 3D printer fluid. It's this, I don't know if it's a fluid. It's just the printer material. All right, we want to feed that material into the printer. And what we found out is that the tower is going to be built beneath itself. And it takes 1 kilogram of printer material, or this printer fluid, think of it as like a glue or something, to gain 10 centimeters in height. Okay, so we should note that 10 centimeters is actually 0.1 meter, right? It's a tenth of a meter. So the question then is, how much work to gain 10 meters, and that's basically the tower. For this problem, we'll neglect the actual weight of the printer. So really, basically, the question then is, how much work to move the fluid up to height y in order to add a layer. Okay, so that's the basic question, and what the idea here is, if here's our tower like this, right, each layer gets added on, and okay, of course the first layer, there's no work involved because you didn't actually move up any mass up gravity, right? But then, you know, after the 10th layer, you know, you have to climb, or I shouldn't say climb, you have to the mass must climb up to the tower top to get applied. Okay, so the model for this now, this is very different than the case of the previous problems here. The mass is not changing. Okay, the mass of this stuff is always the same. Okay, rather it's how far a given mass must travel up against gravity. So that's really the question that we have to ask. Okay, and then the related question, of course, is how much additional growth do you get for every kilogram? So note, so if 10 centimeters of height is bought by 1 kilogram of printer material, then that means that 10 kilograms of printer fluid or material gets 1 meter. of height. Okay, so I think that's a really key fact here. And with this, we should be able to get this. All right, so I think we have the logic down here to figure this one out. The problem solving shouldn't be too hard from here on out. All right, so what I have to do is get a mass. The mass of a delta y slab of the tower is equal to, well, what is it equal to? We have to figure out what the density is. Okay, so it's actually going to be 10 kilograms per meter, right? Times delta y, how tall, okay? Right? So that's the mass, and that means the force, or I shouldn't say the force, I guess the force of gravity then is going to be, of course, g times that mass times delta y, right? Or, oops, I should back up there, times 10 times delta y, right? Okay. Right, how far is it going to go? It goes y distance. Okay. To go one meter, you need 10 kilograms of this stuff. So what we're going to do is actually talk about the work to go y distance is going to be g times 10 times delta y times y, right? And again, the idea here is that basically if you have a little slab of this stuff and I have to put it, oops, back up there. Here's my tower, and if I have to put that up on top there, it has to go y distance, right? And that right there is the little delta y slab of it. It has to climb up that much, okay? So that means the total work, so we can of course take delta y and turn it into a dy, a little tiny amount. The total work is going to be the integral going from 0 to 10. I want to go 10 meters tall. It's going to be g 10 times y times dy, okay? And of course we can calculate that to be g times 10 y squared over 2, evaluated at 0 to 10, and you get g times 10 to the third power all over 2. So that's the answer of how to build this problem. So here it's not the mass that was changing, but rather the distance the mass had to travel to get up to where it needed to be placed. That was the modeling that had to be done. So I gave this problem as sort of a last problem you do, sort of give you new insight in how these things could work and how modeling can change based on the scenario involved. All right, thank you very much.